Well, thanks again. Thanks very much. And thanks very much to everybody else who was involved in this and to people who were speaking. As Tomer said, this is a set of ideas that are very dear to my heart that we've been working on for a really long time. So it's fantastic to see this new interaction between computer science and AI and developmental psychology really beautifully illustrated by the talks that we've had so far. So I'll get back again, sort of finishing where we began. To Josh's point about this wonderful quote from Alan Turing at the very beginning of trying to think about AI, which was, why not produce a mind that simulates the child rather than producing a program that simulates the adult? And this very old quote has taken on a new kind of significance in the recent AI spring, because of course the reason why you would want to do this, at least in part, is because it would tell you something about learning, since we know that children are the best learners in the universe. And that's exactly Turing's point, that rather than trying to build in particular kinds of knowledge, we might do better by trying to get systems that could actually learn that knowledge in the way that children do. And that's been the strategy that's led to the recent advances in AI. But of course, as we all know, that strategy has had some drawbacks. So if we look at the kinds of learning that's gone on in AI, what we see is that it needs lots and lots of data, point people have made before. Typically, although there's beginning to be changes to this, it needs things like supervision or reinforcement. And there often is not the right kind of generalization. And we were talking about common sense the other day, and I really think this is like the key idea. The key idea is that people in machine learning face this problem of having lots of data and not having the kind of generalization that we would want. On the other hand, it's computationally tractable. It actually works. If you compare that with 4-year-olds or indeed infants learning, as we've heard from a lot of the wonderful talks today, we see just the opposite. So we see that babies are learning from very small amounts of data, and data that's very different from the sort of giant, say, ImageNet data sets that we see in typical AI. They have very little supervision or reinforcement. So if we're trying to mimic them, we're going to have to think about things like self-supervised learning. And they make excellent generalization. And again, Shari's lovely talk is a lovely example of that, where the children are, even babies, are making really striking and impressive generalizations. The problem is that we don't really have a good computational account of how it's possible for them to do it. And in particular, the search problem of how they could look among many different representations and figure out which is the right one, I think is still very, very, very challenging in cognitive science. All right, so how could we solve this problem? There's really two sorts of approaches, as many people have pointed out, that we could think about. One of them is to say the kinds of broad representations that would allow excellent generalization are actually there from the beginning, or they're very early in the form of intuitive theories of core knowledge domains. But the other alternative, and I don't think these are at all mutually exclusive, in fact, they build on one another. The other alternative is that there's also these learning mechanisms that are in place from very early on that we think of at Berkeley as these kind of constructivist learning mechanisms that enable the construction of new abstract representations from small amounts of data. And in our branch of the DARPA project, we've emphasized 3 different such elements. That's where our MESS title comes in, aside from the fact that that's a good characterization of children. One of them is learning abstract novel causal models from statistical evidence. So actually being able to not just have models and causal models, but to actually be able to construct those abstract models given the evidence and data you have, and to construct new ones, including ones that never would have existed either in the course of your experience or indeed in the course of human evolution. And a second piece, which we've also heard about a lot, is the idea of active learning, and particularly active learning through exploratory play. That's something that Eliza's lovely talk told you about, the work that we're doing about that in the context of mazes. And we'd heard some other things like Deepak's beautiful curiosity-based algorithms that speak to that same set of ideas. And then the third one, which I won't get a chance to talk about today, is the idea that children are learning socially. So they're learning through things like imitation and demonstration. So in the brief time that I have, I'm just going to give you one example each of recent work that comes out of our lab that demonstrates something about causal model building, and about active learning through exploration. Now, for the last, I am horrified to think, 20, 25 years, we've been looking at how children understand and learn abstract causal representations. And this was maybe one of the very early interactions between developmental psychology and computation, because it turns out that computational accounts of these kind of abstract structured representations show that you can have abstract representations with systematic relationships to data, and that these are probabilistic models. So they're not deterministic, they're probabilistic, they're abstract, they're structured, and they're causal. And as I say, for 20, 25 years now, we've been showing that we can understand a lot of children's learning in terms of these models. And there have been various advances in our understanding of those models, again, including ones by people who are on this panel and part of this program. So what happens is, because you can point to systematic relationships between the structure of a model, including a model you haven't even really known about or considered before, and patterns of data, that also means that you can use something like Bayesian learning in an inverse way to say, given that I have this particular kind of pattern of data, what kind of causal model could have generated that data? And what we've shown is that, what we and others have shown is that even very young children, 4 years old and younger, can appear to be able to rationally perform this sort of inference from data. And that includes, for instance, in work that we've done very recently, showing that that preschoolers are inferring social concepts, like whether an inequity comes from the circumstances you're in or your innate properties, physical ones, like some of the ones we've talked about today, psychological ones, like the kind of goal orientation that Sherry was just talking about. And children can infer unobserved causal structure, infer abstract over hypotheses, et cetera, et cetera. But today I want to talk about a different kind of representation, causal representation in these models, which we haven't studied, and as far as I know, no one else has. And that's what I'm going to call a causal function, not in the sense of a function of an artifact, but in the mathematical sense. So you could think about a causal function as being something that says, if I have a particular value of a cause, I can say something about the quantitative value of the effect of that cause. And the interesting thing is that if you have this kind of a causal representation, this kind of causal function, you can extrapolate. You can make new inferences about what will happen in situations that are extremely different from the ones that you could actually have observed that would let you infer the function in the first place. And let me give you a kind of classic example of this. So here's Alice. And Alice is her normal 7-year-old little girl size. And she takes a drink from this bottle. And what happens is that she shrinks down to a size that's smaller than a mushroom. And then she nibbles on one side of the mushroom, and she actually grows to be so big that she won't even fit in this house. So what's happened is that in order to understand this sequence of events, and after all, this is something that even young children are very good at understanding and very interested in and find very engaging, this idea of things getting smaller, getting bigger, I can extrapolate to the idea that someone might take a potion that would make them as small as a mushroom, or they could take a potion that would make them as large as a house. Even though this kind of shrinking and growing phenomenon is not something that you're going to be seeing in your everyday experience, and it's not something that, that you would expect that evolution would have built in, because it is a very rare thing in your everyday experience. And in fact, if you see this kind of massive shrinking or growing, the obvious thought would be that something fantastical or magical is going on. But the interesting thing about things that are fantastical and magical is that in some sense, they're still part of common sense. We can still make sense of them. We can make inferences about them. We can make predictions about them. So we can predict, for instance, that your head will be up against the roof if you grow like this. So being able to learn and extrapolate and use these causal functions to reason would give you a particularly wide-reaching capacity to learn about common sense. And now this is all completely Mariel Goddu's credit. Mariel actually figured out how we could ask even very, very young children, toddlers, whether they were capable of learning in this way, learning a novel causal function like this from evidence. And she's going to have a poster session about this that you can talk about, and you can learn all the details. I'm just going to be able to go very quickly through the experiments. So we did this experiment with 3-year-olds and with 24-month-olds, and all of our experiments nowadays are pre-registered. So here's the way the experiment goes. We introduce, Mariel introduces very young children, toddlers, to a music box, and with evidence that there's a particular shape they need that has to fit on an outline. And then they get introduced to 2 change machines. The change machines are such that one door makes the object bigger, one door makes it smaller, like in Alice in Wonderland. And at test, the children have a new problem. They have to decide, they're given a shape that's either too big or too small to fit into the box, and they have to figure out what to do to try and either make it bigger or make it smaller. Again, let me show you how this works. So here's the music box, and some shapes make my toys play music, but if they're too small, they won't work. And if they're too big, they won't work. They have to be just the right size. So this is sort of Goldilocks and Alice in Wonderland. So that's the music box training. And then the children see this change machine, and what happens is you put things in one door and some things happen. You put them in the other door and the opposite happens. In one door, they get smaller, like the 2 sides of the mushroom, and in the other side, they get larger. And actually the way this works is there's a single object, my little friend, the object goes in the blue door and it gets small, it goes in the blue door again and it gets even smaller. So you actually see 2 examples of the function. And then you put the object in the yellow door and it gets a bit bigger, you put it in the yellow door again and it gets even bigger. So you've got 3 points on that functional graph. And now we go back to that music box. Now we've got a new example, and this new shape is actually a lot bigger than any of the shapes that the children have seen before. So in other words, the actual size that they're looking for is not like any of the sizes of objects that they've seen before, but they have to figure out how to make it larger or make it smaller depending on the condition. So they have to decide, do I want this box, the object that I've given you, to be bigger or smaller? And then they get a choice of which door to put it in to make it bigger or smaller. And what we found was that these toddlers are very good at doing this. So whether we ask them to make something that's too big smaller or something that's too small bigger, they're very accurate at doing it. So with a very small amount of data, and strikingly data with objects that are not the same size as the objects that they're generalizing to, the children seem to be able to very quickly infer this function and use this function that they've inferred to solve a new problem. They seem to be able to mentally manipulate it to be able to generate a new inference. And just a parenthetical thing is, I think these kinds of experiments in some sense give you a better, or at least give you a different handle on what's going on cognitively than the kind of classic violation of expectation experiments do. Okay, so that's the first part. So this is children inferring abstract causal models. The second thing that I was talking about was children being able to explore. And we've been working a lot at that as well. And one of the things that's interesting about children's exploration is that many things that you might think of as bugs from the perspective of exploitation, say what a reinforcement learning algorithm would do, are actually features from the perspective of exploration. And this speaks to an old tension between exploration and exploitation, one of the oldest tensions in the literature. And what I've suggested is that some computational features of children in particular make them especially exploratory searchers. And let me give you an example of an experiment that we've done to try this. So this is an experiment like our Liquin detectors. It's a little box that lights up and plays music. But this time there's actually something writing on what happens with this little block, which is that you get stickers. And the way that the experiment works is it uses a kind of reinforcement learning setup where you put a block on the machine, this white stripe block, and the machine lights up and you get a sticker. On the other hand, now you put a black striped block on the machine, and that's not a ZAF, that's the wrong example, so you actually lose 2 stickers. So there's a greater penalty for being wrong than benefit for being right. Now you get another example where there's now you've got another example with an object with white spots on it, and you put it on and it is in fact a ZAF, and it makes the machine go, and now you get another sticker. And now here's the question. Now you have a choice, you have a new block that has black spots on it, and you have to decide in a kind of RL framework, are you going to approach or avoid? Are you going to explore or exploit? And quite a bit of really elegant work. Now, suppose the first impulse, as we'll see, that adults have is to say, well, look, I'm not going to approach. It looks to me like I've inferred a good causal rule here, which is that white things make it go. And this is black, so I won't risk the negative outcome. But of course, if that's not the rule, if the rule is actually this two-dimensional rule, which is that anything that's either white or spotted is a ZAF, then you'll actually lose, you'll forego potential reward that you might have gotten. And this is based on work that Todd Gorekis has done. And what he showed was that if you do this kind of thing with adults, what happens is that the adults get caught in what's called a learning trap. So what happens is that the adults rapidly assume that the one-dimensional rule, the rule that they've got the most evidence for, the one that has the highest prior probability, is the right rule. They are also trying to exploit, so they avoid things that would be wrong according to that rule, but the result is that they don't actually do the kind of testing they would need to find out that this other more unlikely rule was the case. So here's the result from the adults, which is very much like Gorekis's results. So you can see that the adults are only approaching half of the positive valence blocks. But if we look at 6 to 7-year-olds, they actually are approaching the blocks. They're actually more likely to approach the blocks than the adults are. And if we look at 4 to 5-year-olds, the 4 to 5-year-olds are very likely to approach the blocks. And again, if you think about your average 4-year-old in this situation, the 4-year-olds just really want to see what happens if you put the blocks on the machine. So in a sense, things that you might think of as bugs, this kind of impulsiveness and curiosity that you see in these young children, actually means that they're getting more data. Now, of course, the crucial question is, are they actually using that data that they've gotten through exploration to solve the problem? So what we can do is just at the end ask, what do you think the rule is? Do you think it's this one-dimensional rule like color or shape of the dots is the thing that makes the machine go? Or have you inferred this actually initially unlikely rule, this two-dimensional rule, that you have to take into account 2 features of the object to decide whether it's a ZAF or not? And what we discovered was, again, across 2 different experiments, I'm just going to give you one set of results. What we discovered was that the adults, as in the Gorekis experiments, tended to learn the one-dimensional rule. The children were learning the two-dimensional rule. So not only were the children exploring more, but the children's extra exploration was actually enabling them to get information that then enabled them to learn more. And there's some lovely work in the comparative literature which suggests that even if you look at young juvenile rats and mice, for example, unlike adults who classically do avoidance learning, where they won't go to a place where they've had to take a risk, in fact, the young rats are actually preferring to go to the place where they've had the negative outcome. Because like our children, even though you're losing the stickers, you're gaining information. And that gain in information actually enables you to learn things that you wouldn't otherwise be able to learn. So from this perspective, things that might seem cognitively less than optimal in terms of children's ability actually turn out to have an advantage if you're thinking about how you could manage this balance between exploration and exploitation. Okay, so these are just 2 examples. We have, I could mention a bunch of others from our lab, suggesting that part of the way that toddlers and infants develop common sense, we humans develop common sense, is going beyond just the kinds of abstract theories or the abstract representations that evolution might have given us, to have these kind of constructive causal learning mechanisms. And those mechanisms allow children to both learn and use novel causal functions to solve novel tool use problems, to be able to deal with lots of different environments. And it also means that they're prioritizing both learning and exploration over reward. And the fact that they're doing this is actually enabling them to understand more about what's going on around them. And I think the really fascinating challenge, the things that we're starting to do in the exploration case, for example, is to actually have models of exploration and curiosity that can help to solve these problems. And starting to have representations that include things that are more abstract, like these causal functions, that then can be used to solve problems. So my latest slogan, is that you could think about children as being evolution's way of performing a kind of simulated annealing and resolving explore-exploit trade-offs. This is a new review paper that's in this special issue of the Philosophical Transactions. And really, the point here is that humans in particular, but more sophisticated animals in general, going back to some of the ideas, going back to some of the things that Deepak was talking about, even if we're thinking about the course of evolution, the evolution of creatures like us who have a very long, extended childhood and lifespan might itself be a strategy that helps to resolve some of these problems. And in particular, it's a strategy that helps us to not just learn about the environments that we're likely to be in, but also means that we're prepared to learn about the very wide range of environments that human beings actually create and learn in and understand. Okay, so since I was live, I was not looking at the questions, but I'll stop now and have a few minutes for questions.